All right, guys, welcome to another day. I hope you're having a good morning or afternoon. Anyway, so today we are going to be jumping into some trig limits. And limits of trig functions are usually not a massive deal if the trig function is what you remember graphing. However, a lot of times you're going to get functions that include trig functions, but you're going to have no idea what that graph looks like. So you're going to still have to have a process about how to go about evaluating these things. So what I want to show you first is a lot of what we do, they're going to be some similar properties as far as plugging the value in and seeing what happens. And if I get an answer, awesome. If I get a 0 over 0 or a number over 0, knowing what to do with that. And that's usually what we're going to be talking about a lot of, is how these things behave. So it's important for you initially to understand a couple of properties. And I'm going to go through these properties and show you the graphs of them. But then I'm going to show you that there are a lot of little tricks you can employ. Now, one thing I'm not going to talk about is something called the squeeze theorem. I know there are a couple of you who are like, oh yes, I know the squeeze theorem. You're welcome to go look up. There's some videos on Khan Academy on the squeeze theorem. I am not going to teach it in this course. It's just not what we do in pre-cal at all. And I won't teach it in AB and maybe not even in BC because AP Calculus doesn't require it. Now, at some point they might change that, but until they do, I am not going to teach it. It's pretty cool. I mean, it makes sense, and it's not an overly difficult concept, but I'm just not going to teach it. So I'm going to be showing you a lot of little rules and a couple of little tricks to make your life easy. And if you get these down, trig limits aren't a big deal. If you don't get them down, yeah, they can be a big deal. And then also, when you learn how to do a derivative later, you will learn a process called L'Hopital's rule. And it looks like La Hospital, but no S. But anyway, L'Hopital actually came up with a way to evaluate some limits under certain conditions, like if you get 0 over 0 or infinity over infinity. Things like that, you're allowed to use L'Hopital's rule. But right now, since most of you don't know how to do derivatives, we're not going to learn that. So let me start out by showing you there are these 5 pretty simple limits that I want you to understand. I'm going to show you the graphs of them in case you don't believe me, and then we're going to use these to simplify limits moving forward. All right? So here we go. Okay, guys, so I'm on page 29 in the book, and I'm looking at limits of trig functions, notes, and classwork. I've got a trig limits practice worksheet for you to work on after this. Please check the key. Make sure you understand this. Email me any questions you might have. I'll probably even work some of those as well if something jumps out at me that might be tricky for you. And then tomorrow, there are just a couple of worksheets, no video for you to work with. However, on Wednesday and Thursday and Friday, I'll have videos posted for those lessons and some of the work that we're doing on those. And you're really kind of getting a long review for 3 days, because really after today, we're just kind of we're just going back over stuff. So we're really going to stretch it out a good bit, and then we won't test until a week from today on the 20th. All right, so looking at these, it says when calculating trig limits, remember to consider the following. So if you're reading through 1, 2, and 3, you're seeing basically the same thing we've always done. Whenever you take a limit towards a value like 0 or 5 or pi over 2, although you will see a whole lot of 0 going on, limits to 0 right now as we start this work. But you're going to do the same thing. You plug it in, you see what you get. If you get a value, we're super happy, okay? If we get a 0 over 0, that means there's a hole, and we're going to have to find that limit because limits exist at holes, most likely. We did talk about an exception of that when you cancel the hole and then you get a number over 0 after that, the second time you do the limit. But you typically get holes there. And then also you could get a number over 0, which means there's a vertical asymptote. And if you get a vertical asymptote, we know the graph on either side is going to infinity or negative infinity, and we will often have a need to find that. Although a lot of times with trig limits, we kind of just bail and say D and E, and we don't really overly evaluate them a lot of times because we really don't know exactly what the graphs look like sometimes, because they can get pretty nasty. In that case, sometimes it's okay just to put D and E. I haven't seen questions get really, really brutal, but you'll have a good feel of that by the time we're done. So Anyway, 5 things that we're going to base the majority of our work on are these 5 trig limits. Okay, it's the limit of a sine function, a cosine function, a tangent function, and then a sine of something over something. And that u, it could be x goes to 0. It could be 3x goes to 0. It could be basically anything right here or right here. If those values are the same, if it's sine of like 5x over 5x, it's equal to 1. If it's 10x over 10x, equal to 1. And then the same thing if it was like 10x over sine of 10x or 5x over sine of 5x, always equal to 1. As long as those match, these limits will be equal to 1 along with this one, and these will be equal to 0. Now, I want to show you how you would manipulate some of the math to get there. So I've actually worked out the first 4 problems, so you don't even have to take notes. But looking at this first one, you see this limit. Well, anytime you see a limit, I'm going to go ahead and zoom in on this a little bit. Okay, so anytime you see a limit, we know we just plug the number in. Okay, so we're going to plug that 0 in there, and we get 2 times the sine of 0, and we know that the sine of 0 is 0, and 0 times 2 is 0. So all of that's going away. And if I plug a 0 in there, we know that the cosine of 0 is 1, and 1 times 3 is 3, and 0 plus 3 is 3, and I got an answer, and I'm happy. Okay, and literally what I've done here, even though I didn't acknowledge it, remember we talked about very first day, it's been a while, but if you look back at the first page of notes, a limit of 2 functions added together is the same thing as the limit of each function. And you are allowed to factor a constant out. So really, this is like I'm just finding the limit of sine of x. Well, that's this rule right here. The limit of sine of 1x is 0. And 0 times the 2 that you factored out is 0. Right here, the limit of cosine x. Well, the limit of cosine of 1x is 1. And by the way, it doesn't matter what that a value is. A value could be 10 on either of these. On the inside, as a coefficient of x, it's still going to be equal to 0 and 1. All right? So anyway, when I take the limit of the cosine x, I get a 1, and a 1 times 3 is a 3. But if I just plug it in, I kind of see the answers, and I'm in good shape. And just to show you that on a graph, I think you know what the sine curve looks like, but it makes sense that a sine curve, no matter what the value is, I have an a value of 1 here, but look, as I approach an x value of 0, the limit is 0. Okay, you can see that it's approaching 0. And look, even if I change that a value to 9, when I graph it, I might get a lot more action, but what's happening at 0? The limit is still 0, and you can see that, okay? Now, and then the cosine value, check it out. If I turn that graph off, I know I'm using a different calculator, but this one kind of works well this way. It's kind of quick. Here's your cosine curve, all right? And a cosine curve, what do you see? As x approaches 0, the limit is up there at 1, all right? And it doesn't matter whether it's 1x. If I change that to 8x, 12x, whatever, and graph it, I might increase the number of periods that occur in that or shorten the length of the period. But look, it's still, as x goes to 0, the y value is still 1. Okay? And then the same thing occurs with the tangent graph right here. Plus, you can think of tangent as sine over cosine, and 0 over 1 is 0. But I will go ahead and just show you this. The tangent graph, all right, obviously looks like, there you go. As x approaches 0, the y value approaches 0. The limit of that function is 0. So you can see that the tangent value is also 0. And again, that doesn't matter. Putting this in here just changes the length of my period and puts more of the little squigglies in there. Now, the ones that you might need some verification on are the last 2. You probably don't know what those look like, so let me just show you. Here's a sine of 3x over 3x. All right, it just wiggles along like that. All right, but you can still see again, I'm graphing sine of 3x over 3x. All right, so you can see that function, sine of 3x over 3. Well, maybe you can't see it, but whatever. But you can see as x approaches 0, the y value is 1. So right there, sine of 3x over 3x ends up being actually, this is not sine of 3x over 3x. If it was sine of 3x over 3x, I'd get a 1. This particular one I graphed was sine of 3x over 3x, but watch, even if I change it to 8x over 8x, you can still see, you might get a lot more squiggles, but look, it's still, well, and I know right there, you're looking at this and going, well, it doesn't quite hit. Well, that's because my window, this is a weaker calculator, if I change my resolution or my change in x to a much smaller number, you know, my graphs end up being, what the heck? X min, oh, sorry. Positive 2 pi. I don't know why I hit that accidentally. You can see it. It'll get a little bit closer to that. But basically, there's a hole there. Okay, so the graph actually does hit at 1. It's a little bit of a weakness in this calculator. But remember, there's a hole there. If I plug a 0 into this function, I get sine of 0, which is 0, over 0. And 0 over 0 is not equal to 1. 0 over 0 is a hole. But this property right here, because of what I know about it graphically, I know that it's going to have a height of 1 there if these two things match. Okay? And then the same thing with this. I'll go ahead and graph that to humor you. And then after this, we're not going to do this anymore. So I'm just, here we go. Here's the other graph. It's doing some unique things right there, and that's all I see of it. But look, you can see again, it comes down and actually hits. It actually hits a y value of 0. Now, it looks like it's actually at the point there, but there's still a hole there. Look, if I plug on this graph right here, if I plug a 0 in to this function or this function, I get 0 over sine of 0. 0 over sine of 0. Well, sine of 0 is also 0. So 0 over 0 is not 1, right? 0 over 0 is undefined. There's a hole there. But when I have holes, I have limits. So I have learned, because of the graph of this right here, I know that because of the graph of that, looks like this. And look, even if I go trace and enter a 0, look what you get right there. You get nothing. Y equals blank. There's nothing there. But there is a hole there, and I'm approaching that y value of 1. So bottom line, guys, you just need to memorize those 5 little rules, and then I'm going to even show you some better tricks later that I think will help you out. Okay? So first thing, let's look at we've already looked at number 1, and I plugged a 0 in there and got a 3. Well, let's look at number 2. Number 2, if I plug a 0 in there, I get 0 plus 1 is 1, and then I get 1 minus sine of 0. Well, I know that sine of 0 is 0, so I end up getting 1 divided by a 1, because all of that's a 0 as well, and that equals 1. Well, anytime I get an answer, I'm happy. It's when I don't get answers that I'm not happy. And that begins here at number 3. So, sorry about that. So here we go with number 3. Number 3, we get sine of 3x over regular x. Now, I'm going to show you a trick for that in a second, but I want to show you how your calculus professor might expect you to do things. Okay, there are certain properties that you'll prove in calculus using the squeeze theorem, and they are typically these two. So we usually try to get things back to these two, and if I can, unless you want to prove even more and more properties, you can always do all of our trig problems just by rewriting stuff in terms of these 5, but particularly these 2. All right, so let's check it out. Number 3 is really close to that 4th rule, sine of u over u. Problem is, it doesn't have that 3 on the bottom. Well, I have an algebra rule that says I can multiply the top and the bottom by a 3. And if I do that, I could take this 3 and pull it over with that x and call it sine of 3x over 3x. And remember, from the first day, you have a property that says if I have a product, I can take the limit of each of these. So I'm going to take the limit of the first part, and by rule, sine of u over u, sine of 3x over 3x, because those match, this part's equal to 1. So I've got that limit done. And then the second part, sine of 3, that's just saying when y equals 3, what happens when x approaches 0? Well, if y is 3 all the time, a limit of a constant is always a constant. So we've evaluated this limit, and I get a value of 3. Okay? Now, this next one's a little trickier. Tangent of 4x over 5x isn't even close to a rule. Okay? So what I do on this one is I am going to take this 5x, and I'm going to slide it out to the side, and I'm going to change this to a 1 over a 5x. And you can see that right here. And then I'm going to take tangent of 4x and rewrite it as sine of 4x over cosine of 4x, because we learned that in trig, that a tangent was the same thing. Tangent of an angle is the sine of the angle of the cosine of the angle. Now, at this point, I am going to take the cosine of 4x, and I'm going to slide it over to the right where this fraction is, and you can see me do that here, okay? And I'm going to take this x, and I'm going to put it under the 4x. So the cosine of 4x slides over, and then the x slides over here, and that gives me that. okay? But at this point, when I put that x under there, all I have is sine of 4x over a regular x, okay? And if I have a sine of 4x over a regular x, I've got to deal with it a little bit. Sorry about that, I had a barking dog. So what I have to do to fix this is I have to, like I did before with putting the 3 over 3, I'm going to put a 4 over 4 in there. And when I put the 4 over 4 in there, what do I see? I see a sine of u over u. Okay, now again, I'm going to show you some shortcuts to these, but I want to show you kind of a calculus teacher in college's approach to doing this first. Then I'll show you the tricks, and this will become you're going to look at this problem in about 5 minutes and go, oh, I get 0 over 0 when I plug that in, so 4/5. Okay? Oh, and by the way, initially, I always want to check that. If I plug a 0 in there, 4 times 0 is 0. Tangent of a 0 is 0. That's our third rule above. That gives me 0 on the top. And then 5 times 0 is 0. And it's when I get 0 over 0 that I need to employ these rules. Okay, remember, like in problems number 1 and 2, if I get an answer, I'm good. It's when I get 0 over 0 that I need to employ these rules. And that happens in number 3, and it happens in number 4. So at this point, going back to where we were, I can evaluate this. If I plug a 0 in there, again, I get 0 over 0, but this is a rule. This is rule number 4 above, the sine of u over u. So all of this part right here ends up giving me a limit of 1. Okay? Now, this other part, I can now take the limit of that. That's what I'm doing right here. And if I plug a 0 in there, what's 4 times 0? 0. What's cosine of 0? 1. What's 1 times 5? 5. And I end up with 4/5. So this big problem ends up being 1 times 4/5. All right? And again, much harder way to go about doing it, but if you had to show your work, I had a kid I ran into at an Auburn game, told me his teacher was making him do this. And they had to prove this property right here using the squeeze theorem to even be able to do this. But that just depends on what calculus teacher you have. All right? In college. Or if hopefully you'll pass the AP test and not have to worry about it. All right, what about number 5? Again, always plug the 0 in. If I plug a 0 in, I get 2 times 0 is 0. If I plug a 0 there, I get 0 times 7 is 0. Sine of 0 is 0. And then once again, I have 0 over 0. So I know there's a hole, which means I know there's a limit. All right? Or 99% of the time. And these trig problems, almost 100% of the time. So what am I going to do? Well, this kind of looks like the 5th rule up here. The u over sine of u, except these numbers don't match, right? They have to be exactly the same for this to be true. So what could I do to make these numbers match? Well, I could multiply by a 3.5 and a 3.5. Now, if you can't see that I multiply by 7 halves and 7 halves, then do this. Go ahead and factor the 2 out so it's not there, and then multiply by essentially a 7 over 7, okay? And then we're just going to move that 7 in, and that just leaves me a 1 over 7. And if you want to at this point, you can even bring the 1/7 out. I don't really need that. I'm just going to take the limit of each part of these, and when I'm done, multiply by a 2. So here we go. I'm going to drop the 2 down. What's the limit of 7x over sine of 7x? 1. Bring down the 1/7 because the limit of a constant is that constant. And what do I have left? 2/7. All right? And again, I'm going to show you some better ways to do this as we go through there. But here we go. All right, what about this one? I plug a 0 in, I get 0 plus sine of 0. Well, sine of 0 is also 0. So I got 0 on the top and 0 on the bottom. So again, I've got an issue. 0 over 0 is a hole, but I got to go find it. Now, this doesn't follow any of those 5 rules, but you do know that when you have a fraction that has the numerator with 2 parts being added or subtracted, I'm allowed to do this. Break it up. Now, again, I don't want to do this if I get an answer. I only want to do it if I get 0 over 0, which I did. So I'm going to rewrite this as the limit of x over x, which is 1, plus the limit of sine x over x as x approaches 0. All right? And when you see this, you're like, oh, well, the limit of a constant is a constant, because again, this is like the y equals 1 function. It's always equal to 1. And then the limit of this follows that rule, the 4th one at the top, the sine of u over u, because those match. I know that that's all equal to 1. So 1 plus 1 is 2, which you've known for a long time, right? All right, look at number 7. Number 7, when I plug a 0 in, I get tangent of 0, which is 0. 0 squared is 0, and 2 times 0 is 0. So again, 0 over 0. So what do I do with that? Well, this is not a rule. This is tangent squared over 2x. I don't even have that in one of my top 5. So what I need to do is break this tangent problem up. So I'm going to take this, and I'm going to rewrite that tangent problem. I've got tangent x. That's what tangent squared x means. So I'm going to write tangent x and then another tangent x, okay? But sadly, I only have 1x and 1, 2. So you can leave the x here if you want. You can put the 2 there if you want. There's a lot of different options here. But what I'm going to end up doing is putting one of the x's there, one of the ones there, and I'm just going to take this constant and pull it out to the side. Okay? Does that make sense what I'm doing? Because that's 2x on the bottom and tangent times tangent on the top. Okay? So at this point, in fact, if you want, you can take this x and do something with it. But at this point, I'm going to rewrite this tangent as sine over cosine, and this tangent as sine over cosine. And again, I'm going to show you some tricks on this in a second. Okay, so this tangent right here is sine x over cosine x, but you still have this x right there. I'm going to put it out to the side. This tangent is sine x over cosine x, and you still have this 1/2. So I have completely split this guy up right here. And then at this point, I'm looking for rules I can use. Well, these aren't really rules I can use, but what if I put that x under the sine x? Basically switched spots, all right? So that gives me a sine x over x, which is a rule, right? And then right here, I'm just gonna treat this like a regular sine x. That's a rule. And I'm gonna bring this over like this. And I'm basically dealing with 4 separate limits. But the reason why I'm not worried about these is because when I plug a 0 in for cosine and for x for cosine, I get 1. So I'm not getting undefined terms here. I'm getting zeros or undefineds here. But now, look, this is a rule. This rule set, this is our 4th rule up there, sine of u over u. Because those match, that's equal to 1. When I take the limit of this and plug a 0 in there, I get cosine of 0 is 1. 1 over 1 is 1. When I plug a 0 in here, I get sine of 0 is 0. And when I plug a 0, which means the whole thing's going to be 0 as long as this is not undefined. When I plug a 0 in here, I get cosine of 0 is 1. 1 times 2 is 2. And 1 over 2 is 1/2. But at this point, you can see that this is equal to 0. All right? This one's very similar to number 7, except I have 2 tangents and 1, 2, and 2 x's. Now, I've seen people look at this 2 and go, you know what, that 2 is just in the way. I'm going to go ahead and bring it out and just leave it as a constant on the outside and deal with it later. And that would leave me this. The limit of this tangent times another tangent times a 1 over x and a 1 over x. And you could leave the x's there for now if you want, but whatever. So this is where I am right now. And then each of those tangents becomes a sine over a cosine. Everybody with me so far? Oh, by the way, what I failed to do at the beginning again was plug the 0 in. When I do that, I get tangent of 0, 0, 0 squared is 0. 0 squared is 0 times 2 is still 0. And because of this, this is why I'm searching for rules. Now, you can see at any point now, I'm still undefined if I try to plug a 0 in. But look what happens if I take this x and switch it with cosine, and this x and switch it with cosine. Now I have sine x over x. Sine x over x. These cosines end up being on the bottom. And remember, cosines don't give me issues, do they? When I plug a 0 into a cosine, I get a 1. So look, now I have rules. Sine x over x, both of those are equal to 1. 1 over cosine of 0. Cosine of 0 is 1, so that gives me 1. That gives me a 1. And don't forget, I still have the 1/2 on the outside. So all of this ends up being 1/2. Oh, man. Dang it, you missed all that. Here, I'll run through that again. Sorry about that. You've probably been laughing and mocking me at this point. Again, when I plug a 0 in originally, I get 0 over 0. I break the tangent up. I take the x's. I make those individual fractions. Remember, at any point, if I plug a 0 in there, I'm still undefined, which means I'm having issues. And so I change that to sine over cosine, and then I put that x under there and that cosine under there. I'm basically reordering these. And now look, I've got a rule. Both of those are equal to 1. Don't forget I can drop that 1/2 down because I factored that constant out. And then when I plug a 0 in here with the limit, cosine of 0 is 1, so 1 over 1 is 1, 1 over 1 is 1, and the whole product gives me a 1/2. Okay? All right, and then lastly on number 9, we'll look at this thing, and then I'll get into some tricks with you that are going to make your life significantly better. You'll really like them. And but again, your calculus professor, if you don't pass the AP test, which again, you guys should pass it. If you don't, shame. I'm just kidding. But you guys should pass it. But if you do, you won't take Cal 1, and then you won't have to worry about these tedious little things. So right here, if I plug a 0 over 0 in there, 0 times 5 is 0, tangent of 0 is 0, 0 times 2 is 0, tangent of 0 is 0. So again, because I get 0 over 0, I'm going to split this thing up. Now check it out. This limit right here, I'm going to take this tangent and change it to sine of 5x over cosine of 5x. That's the tangent on the top. And then the tangent on the bottom, I could, if I wanted to, put it on the bottom and write sine of 2x over cosine of 2x. But I'm just going to take that fraction that I would have written down here and multiply it by the reciprocal. And that gives me cosine of 2x times the sine of 2x. All right. And at this point, I'm going to do some creative math here. Okay, so here's what I'm going to do. I am now going to take this cosine and this cosine and pull them out. So I'm going to leave the sine of 5x here. I'm going to leave the sine of 2x here, but I'm going to pull out the cosine of 2x because that's going to give me a 1. I'm not worried about that, and the cosine of 5x. Okay, so this is the same thing, just rewritten. And now I need some x's in there to make these rules work. So what I'm going to do is I'm going to put a 5x in there. Actually, I'm going to put an x there and an x there because I'm multiplying the top and the bottom by an x, right? But I need a 5. So I'm going to put a 5 there on the top and a 5 there on the, 5 there on the bottom, 5 there on the top. And I'm going to put a 2 there on the top and a 2 there on the bottom. And do you see what I've done? I've made a rule. This is sine of u over u. This is u over sine of u. Both of those end up being 1. When I plug a 0 in here, I get cosine of 0, which is 1 over cosine of 0, which is 1. But I also have this 5/2 out here. So all of that multiplied together gives me 5/2. And that is the long of how you do trig limits. And believe me, they can get uglier, but you're constantly in a search to try to take undefined situations, if they are, and rewrite them like this. Now, we haven't even talked about yet what to do when it's a number over 0. Those are vertical asymptotes, which means the limit is definitely not going to exist, but we usually try to find out more about it, but we'll talk about that in a second. All right, so flip these over, and I want to show you some tricks here. I'm going to have to zoom out on this to see all of this at once. Okay, so this is pattern recognition. I remember my teacher in college, actually, teaching these trig limits, and I kept doing this squeeze theorem and using these things that I'd already proved. I kept doing them like, wow, this is so tedious. So I started noticing some patterns, and that was this, okay? I don't want you to memorize this, but I've written down a whole bunch of different situations here, and I'm just going to slowly walk you through them. This one right here that I'm pointing at is sine of ax over bx. You'll notice that these two numbers are not the same. But what I started noticing is on all of these that I have a box around, you'll see all of those, especially the top 8 that have boxes around them. These are all limits that gave me 0 over 0. And when I finished doing all the math, I noticed that my answer was a over b. And looking back at this, I'm like, wait a minute, the a over the b, those are just the coefficients of the x's. And that was true whether sine of something x was over something x, whether something x was over sine of something x. It was true whether tangent of something x was over something x, or something x was over tangent of something x. Now, again, this is if I'm getting 0 over 0. So you got to check that first. Well, that really made my life easy because now I don't have to rewrite all this junk. I don't have to rewrite that one. I don't have to rewrite that one or that one or that one or that one or this one. None of these I have to rewrite, because if it falls under these situations where you get 0 over 0, all you got to do is take the A and put it over the B. And that's even true if you have a sine over a tangent or a tangent over a sine. Now, if it's anything else, you're not getting 0 over 0. Like if it's cosine of AX over BX, you're not getting 0 over 0. You're getting 1 over 0. That's a VA. At vertical asymptotes, limits don't exist, right? Well, unless maybe the bottom's, well, the limit does not exist ever. But if the bottom was squared or absolute value, well, then I could say, oh, well, since the top's positive, it must be going to infinity. If the top was negative, I'm going to negative infinity. But in this case, I'm checking from both sides to determine what's happening. And unless the bottom is squared, I can just flat out go D and E. This one, I don't even get a D and E. I get 0 over 1, which is 0. And I'm happy with that. Okay, and this one, I get 1 over 1, which is 1. You can see down here, I get cosine, when I plug a 0 in there to the cosine of the sine, I get 1 over 0, which is D and E, right? Because there's a VA there. And here I get 0 over 1, which is 0. I don't have any issues with these in the middle, because I actually get either an answer like 0 or 1, or I get a number over 0, which means there's a VA and the limit doesn't exist. The only one that's a little tricky here is this one. You're welcome to go and graph that thing. If you graph it, you will see that it approaches 0 there. You're just going to have to memorize that for now, which for your test, since this year the notes are open due to the corona. So in this particular situation, because it's the coronavirus year and you have open notes, you might even not have to recognize it. Although I got to tell you, if you're having to look through your notes, you're going to struggle getting things done on this test. So I'm now basically saying, if I get 0 over 0 and it fits one of these 8, I don't have them memorized, and this is what I have in my head. If it's a trig something x over something x, that takes care of that, or if it's a something x over trig something x, or if it's a trig something x over trig something x, whether they match or whether they don't. If it's any of those situations, now no exceptions, I can't have a squared tangent or a squared x, can't have that stuff. But if that's the case and I get 0 over 0, it's A over B. All right? Now if it's not a perfect fit, you got to tweak it a little bit. So let's try these rules. Look at number 10. So I look at number 10 and I'm like, oh, wait a minute, tangent of x over 2x, but it's squared. Well, that's okay. I can rewrite that. So I'm going to rewrite this limit as tangent x over 2x with one extra tangent left over. Okay? So I have the limit of both of those. Well, this is now a rule. The tangent of x over something x, all you got to do, because that gives me 0 over 0, and again, I know that I'm getting a 0 here because tangent of 0 is 0, 0 squared is 0, 2 times 0 is 0. So I'm doing this because of this. I'm rewriting it. And then look, this right here, according to my rule above, is equal to 1 over 2, A over B, 1/2. And this is a rule from the prior sheet. Well, actually, I don't even need a rule. If I plug a 0 in there, what's tangent of 0? 0. So 1/2 times 0 is 0. Now, you'll notice on my rules above, I don't have any mention of cotangent, secant, and cosecant. And I wrote this at the top of the page. So if you ever see a cotangent, a secant, or a cosecant, go ahead and rewrite those as sine, cosine, and tangent. Use that reciprocal identity. Because if you try plugging into a cosecant, cotangent, or secant, you're going to get a lot of undefined stuff that doesn't fit this model. All right, and it's going to be a lot trickier for you, and you're going to have to do it the original way we were doing it, which is a nightmare. So I'm going to right now just rewrite cosecant of 4x as a sine of 4x. But I'm not bringing the 3x down. The 3x is fine. It's that's got to turn into a sine x. So it's no longer here. It's now sine of 4x. All right, well, look, I got a rule. Something x over trig something x. If I get 0 over 0, which I do, plug it in, I get 0 on the top, 0 times 4 is 0, sine of 0 is 0. Because I got 0 over 0, I can just take my A over my B, call it a day. And once again, I didn't show you my work. Man, sloppy. One more time, I'm taking that cosecant of 4x, I'm bringing it down, I'm making it a sine of 4x. The 3x is fine. It's only connected by multiplication. It's not part of the trig function, so leave it alone, all right? And then when I plug the 0 over 0 in there, you can see I get 0 over 0. So now I have a rule. Something x, trig something x, A over B. All right? What about this one? Well, this is a rule except for that constant, right? I could take that 5, swing it out, or just treat it like its own separate function, right? So the limit of a constant is 5. And what's the limit of sine 7x over 2x? Well, trig something x over something x, take the coefficients. So multiply that 5 by the 7 halves, and I get 35 halves. All right? Check out number 13. All right, you're looking at number 13. Hopefully the thing that jumps off the page on number 13 is that squared. That squared means it's not a rule for you. So I am going to have to break it up a little bit. So I have the 3, it's fine. So I have a sine of 5x, right? And then I have another sine of 5x, but I only have one 2x. So just pick where you want to put it. All right. So, and you could put the 2 under the 3 if you want, whatever. You could put the x here and the 2 there. It doesn't matter to me, but whatever. Let's check it out. Okay, so I have these 3 functions, and I'm taking the limit of each of these. So the limit of the 3 is 3, right? The limit of the sine of 5x over 2x, that's a rule now, right? Trig something x over something x is 5 halves. And then the limit of this, where I plug a 0 in there, 5 times 0 is 0, sine of 0 is 0. So all of that ends up being a 0. All right, a lot of people start looking at problems like 10 and 13, and they go, oh, so if it's squared, you're just going to get a 0 every time. No, not necessarily. Take a look at 14. So at 14, I have, again, squareds on the top and the bottom, so I'm going to rewrite that as a tangent x, and I'm going to rewrite that as a, there's only one 2, though. It's not the quantity 2x squared, it's 2 times x squared. So I'm going to put a 2x there and then an x there, and then I'm going to take the limit of each of these. So the limit of the first one, well, once again, you get, and again, guys, on all of these, I'm getting 0 over 0. I'm doing that in my head. But you got to make sure that you're doing that, because when you get down to a problem like number 17 or a problem like number 18, you're not going to get 0 over 0. So you got to be really careful not to just get in the habit of grabbing a over b every single time or rewriting it and then grabbing your a over b. You got to make sure that you're getting 0 over 0, and I did here. That's why I'm doing these rules. So now when I evaluate that limit, because of my new little tricks, trig something x over something x, 1 over 2. This, 1 over 1. So my limit is a half. All right? And then right here, I can ignore that constant, not ignore it, but like treat it like its own separate limit. The limit of 3 is 3. And look, trig something x over trig something x. If I get 0 over 0, which I do because the sine of that gives me 0, the tangent of that gives me 0, 0 over 0. Because of that, I can just grab the coefficients, and I get 15 halves. So again, I've been a little sloppy and not actually plugging the 0 in and writing 0 over 0 there. I don't need you to actually do that and show that like this. You don't have to do that, but you need to actually make sure that that's the case. Okay, number 16, I can't have cotangent right here, so I'm going to take that cotangent of 5x, and I'm going to rewrite that, I'm going to rewrite that as a tangent of 5x in the denominator, and that's going to become a tangent of 2x in the numerator. Now, if there were coefficients out front, leave the coefficients out front of the trig functions alone. They're not part of the trig function. But if it's inside the trig function, they have to follow it down to the bottom. And I think you know that, but I see errors like that every year. Now look, trig function x over trig function x. That's a rule. So a over b, 2/5. And you really are making short work of this. Now, every year I have somebody on the test go, oh, trig something x over trig something x, 3/4. But right here, when I plug a 0 in, I get 0 over 0. That's why I was allowed to use this rule. Here, when I plug a 0 in, I get cosine of 0, which is 1. Cosine of 0, which is 1. Well, 1 over 1 is 1. I don't go 3/4 on this because I never got 0 over 0. Same thing with 18. 18, again, the 4 and the 5 are not part of the trig function. So I'm going to leave the 4 there, leave the 5 there. But that secant 3x becomes a cosine of 3x. That secant of 7x becomes a cosine of 7x. And now when I reevaluate my limit, which I can now because I don't want to try it here with the secants in there, I get 4 times cosine of 0, which is 1. Oh, 4 times 1 is an actual number. And then 5 times cosine of 0, which again is 1. So I actually end up getting 4/5 on that, not 4/5 times 3/7. Now, if that had been a cosecant, which changed to a sine, then I would have had 4/5 times, not 3/7, 7/3. I would have had 4/5 times 7/3, but not with these. All right, so be careful. Make sure Make sure that you're checking all these. These values right here give me 1 when I apply that limit, and all I have left is that 4/5. All right? I'm going to keep on going through this. This is trig limits practice. All right, this is going to be your homework for tonight, but I'm just going to randomly do a couple of these. Something like this, pretty easy. Plug a 0 in, cosine of 0 is 1, 1 over 1 is 1. All right? Something like this, plug a 0 in, sine of 0 is 0, but I'm adding 1 to it. Cosine of 0 is 1, but I'm adding 1 to it. I get an answer, I'm fine. Right here, that's a rule. Trig function, it's something x over trig something x. If I get 0 over 0, which I do when I plug a 0 in there, I can use the coefficients. All right, number 4, plug a 0 in there. Again, sine of 0 is 0 over 0. I can use the coefficients because I got 0 over 0 initially. Same thing here. I can use those coefficients because if I were to plug 0 in there, I would get 0 over 0. So 2 over 2 is 1. Now this one's a little uglier, so I'm going to take my time on it. All right, plug a 0 in there and I get 0 minus 0. Plug a 0 in there and I get 0. So I get 0 over 0. I know there's a hole, but it looks a little weird. Well, again, if I'm adding on the top of a fraction, I can put that over that and that over that. So I'm going to initially start by putting 2x squared over the sine x and x over the sine x. And I'm going to write the limit like this, but I'm thinking about it as 2 separate limits that I'm going to later subtract. Okay? Now, this one, that's not a rule. I can't have an x squared. So I'm actually going to say times, I'm going to take one of those x's and just put it out to the side. Okay? So I've rewritten it now. And by the way, let me take a moment to say, if I have 2 things added in the denominator, like on number 8, you cannot take the top over 1 and the top over sine. You can't split it up that way, although you can take each part in the numerator and put it over the denominator if you need to. So right here, I'm going to take the limit of this times the limit of that, and then subtract the limit of that. Well, what's the limit of this first part? Well, that's a rule, right? 2x over sine of x, 2 over 1. And again, that's equal to 0 over 0. That's why I can do this. Well, this one's not equal to 0 over 0. This is equal to 0 over 1, which is 0. And then this is equal to 0 over 0, so 1 over 1 is 1. So I end up with 0 minus 1, which is negative 1. So some of these can get a little tricky. You just got to keep plugging away with them. We mentioned number 8, so let's look at number 8. If I plug a 0 in there, I get 0 plus 1 is 1, and I get 1 minus 0 is 1. So some of these look ugly, but again, if you're just plugging it in there like you should be getting things that are okay for you. I'm going to jump down to, how about number 15? You're looking at number 15 here, right here. 3 sine 4x over 5x. Well, the 3 is a constant. I can treat it like its own limit. So when I evaluate this, the 3, limit of 3 is 3. And then look, sine of 4x over 5x. Use the coefficients 4/5, and I end up with 12/5. All right, jumping down to number 16, very commonly missed question. People look at problems like 16 and they go, oh yeah, 4 times a 3/5. But wait, if I plug a 0 in there, 3 times 0 is 0, but cosine of 0 is 1, and 1 times 4 is 4, and 5 times 0 is 0. What does that mean? Well, that's a vertical asymptote, right? Is the bottom squared? No. Well, then this limit does not exist. All right? What about this ugly mess on 17? 17, I don't like to divide by a fraction, so I'm going to multiply by the reciprocal, which would be x over 5. Looks a lot better to me now. And that way I don't get an undefined in the denominator right there, which is weird. So now when I plug it in there, I get 0 times 0 over 5. And we know that 0 over 5 is 0. And then looking over at 18, pretty simple. I get a 0 on the top, a 0 on the bottom when I plug it in there. And because it's a trig something x over trig something x, and I got 0 over 0, I can just grab the 7/3, which if you think back to that first page we were working on, this is a much simpler result than all the work we had to do prior to that. All right, let me see what else is interesting here on these. How about number 22? Well, 22 is not bad. How about 29? I see people a lot of times right off the bat on 29. They think, I'm going to zoom in a little bit. on a 29, they look at it and they go, oh man, on 29, why don't we just split it up right now? Well, you haven't even bothered to check. Again, you have to check. If I plug a 0 in there, 2 times 0 is 0. Cosine of 0 is 1. 1 squared is 1. 0 on the bottom. 0 times 3 is 0. 0 squared is 0. What does that mean? That means there's a VA because it's undefined right there, and there's a number on the top. What happens at a VA when the bottom is squared? Oh, it's going in the same direction. All this stuff from the last test. So which direction, up or down? Well, the top's guaranteed to be, the bottom is guaranteed to be positive because you're squaring it, and the top is always going to be really close to 1, so must be going up on the top and the bottom. Must be infinity. All right? And, but then this problem here on number 31 looks almost exactly the same, but there's a sign in it. Check it out. Plug a 0 in there. You get a 0. Sine of 0, 0, 0 squared is 0. 0 times 3 is 0, 0 squared is 0. Now I got to go to my rules. So what do? I split up that sine of 2x. I have two 3x's. So I'm going to take the limit of this now. And what happens when I take the limit of each of those? Well, they both are rules now. So 2/3 times 2/3 is 4/9. All right. So guys, I want you to just plug away at this. I've given you a lot of limit problems to work on. I mean, quite a few if you keep looking. Some of them are, hopefully they don't repeat. I hope I didn't have some copying and pasting errors, but a lot of practice on there for you to get done. Hopefully you'll be in good shape. Email me if you're not, and good luck with this.